So, hello everyone. People have been talking about Fibonacci sequences this week for varying reasons. So I thought I'd do Fibonacci sequences. So we need to start with the definition. So let's, I don't know, let's import tactic. The Fibonacci sequence. Normalize such that fib5 is 5. That's the correct normalization of the Fibonacci sequence. So let's do it. So this is fib from the naturals to the naturals. And how are we going to define it? And I guess the trick is we can use Lean's equation compiler. So we can say where 0 goes to 0, and 1 goes to 1, and n plus 2 goes to obsessive spacing. 0 goes to 0, 1 goes to 1, and n plus 2 goes to fib n plus 1, right? There. And note that I needed, if you don't put these brackets there, then it doesn't work. It's an irritating error, including some kind of incomprehensible docstring issues. So there we go. So there's the definition of fib, and I bet it's computable, right? It's computable. Eval fib5. There we go. Fib5 is 5. Wonderful. We could also eval fib12, right? The 12th Fibonacci, there you go, 144 is 12 squared. The 12th Fibonacci number is 12 squared. So there's the Fibonacci sequence. I don't know, can you reduce? Does this work? That seems to work. Reduce fib12, yeah. Oh, there we go. Can I eval it? I don't normally ever use eval and reduce. Can I eval these things? I don't really know what I'm doing. Apparently, the 100th Fibonacci number is too much for. There you go. You see, Lean's not a computer. In fact, what's going on is that I've implemented a crummy algorithm for evaluation. Who cares about evaluation? I mean, if you want to evaluate Fibonacci numbers, maybe you should try Python. The idea is, we want to prove theorems. And I guess the first theorems you should prove about the Fibonacci numbers are, the first theorems we should prove about the Fibonacci numbers are fib0, which says what? Fib 0, maybe it should be called this. Fib0 says that fib of 0 equals 0, and that's true by definition. I've just remembered that, I've just remembered that about this time last week I spent 10 minutes streaming to nobody at all. So it just suddenly occurred to me that I should actually check that there's a... and then while I'm doing that, fib1 says that fib1 is 1, and that's true by definition. And fib n plus 2, what is this stupid fail to load module? I never quite understand this. I'm not very good at Twitch. Can you reload your module, please? No. Anyway, okay, it's enough Twitch. Let's just assume it's all fine. Fib suck says that fib n plus 2 is, I need an n. This is a thing about natural numbers. And it says fib n plus 2 is fib n plus 1 plus fib n. And no, that's not going to be true by definition, because by definition I put fib n plus fib n plus 1. There we go, and that should be true by definition. Ruffle. There you go. Right. I finally have a chat room. Great. So now what should we do? I mean, so now we need to prove some harder lemmas, right? So I guess one example of a harder lemma is that about Fibonacci sequence. What happens if you add them all up, right? We could do range. What about this? The sum from 0 to n minus 1 of fib I is what? Is, I think it's fib. Let's do an example. 0 0 0 0 1 2 3 5. Right. These are the. Here's n. 0 1 2 3 4 5, and here's fib n. Fib n is 0 0 1 2 3 5. There you go. That looks good. And so the sum. So let's let, I don't know, let's let n be 3. Then the sum from 0 to 2 of fib n is 0 plus 0 plus 1, which is 1, which is fib 3 minus 1. There. So maybe the theorem to prove is lemma trickier. So given a natural number n, you would like to prove, how are we going to do this? I guess we could do range n. What's range n? Is that a thing? Maybe I want list. Maybe, well, maybe it won't be there. Let's do fin set. What about this? Open fin set. Oh, we might even have bingo. Now this looks good. Range n dot sum, because that's fin set dot sum fib. So that's, so what am I saying? Sum from 0 to n minus 1 of fib I equals, well, yeah, we're gonna, you see, I want this to be fib n minus 1, but this is a disaster. This warning bells are flashing. This is subtraction, and that is a bad subtraction, right? Where's my I think this is not a good subtraction. I think this is a natural number subtraction, because fib n is a natural number, and one should never subtract natural numbers because it leads to kind of random results. So I'm going to put this 1 plus this equals this there. So what about this? So 1 add sum from 0 to n minus 1 of fib I equals fib n. There we go. And so now we should be able to prove this. So how are we going to do it? I guess we're going to prove it by induction, right? Induction n with DHD. Okay. And now the first goal says that 1. What does it say? Doesn't look right, does it? That's because this is fib of n plus. I think this is fib of n plus 1. 0 plus 0 plus 1. I see, yeah, n is 3, sum less than 3. Oh, why isn't my example working? It's because fib n is wrong. 0, 1, 0, 1, 1, 2, 3, 5, bingo. And so now n is 3, which is this, great, which is fib 4 minus 1. Wonderful. Let's try proving this. How are we going to prove this? This says that 1 plus 0 is fib of 1, which is 1. So this says that 1 equals 1, right? And 1 equals 1 is true by definition. So this should be REFL. And it is. Super. So that was true by definition. And how are we going to do this case? Well, I guess now we're going to need some. Now we're going to need some interface, right? What's the maths proof? So what are we trying to prove here? So we know 1 plus the sum from 0 to d minus 1 equals fd plus 1 there, and we want 1 plus the sum from 0 to d there equals Fibonacci number d plus, well, I'll just write fib d plus 2, right? So I guess, oh, that's actually, this is the sum from 0 to d, isn't it? And I see. The sum from 0 to less than d, and we now want to, oh, that's kind of crazy. There, and now we want to go from the sum from 0 to less than d plus 1. Okay, great. So clearly the way to do this is we need to change this sum up to d plus 1. We need to change this, so we want we want the sum to less than d plus 1 equals the sum to less than d plus the dth term, right? And that is exactly the sort of thing that's going to be in the library. So I want to rewrite finset.sum range suck is going to be called something like that, right? There you go. So what just happened there was I guessed the name of that lemma because I understand the naming conventions. So finset sum range suck. So now what have we got? 1 plus fib d plus the sum up to d is this thing here. So I guess the next thing to do is this stupid thing. Let's like okay. Let's put this up. Let's put the add 1 on the other side. There, because why not? Oh, I'll tell you what. I mean, we don't even have to do that. We can just switch it, right? We can rewrite it here. Rewrite addcom. Now I've broken my proof. What have I done? Oh, I've left them both there. Let's get rid of this one. There we go. Now my proof is fixed. So finset sum range suck, because now I have fib d plus this sum plus 1. You see this thing here, if I guess there's an issue with associativity, so I can rewrite addasoc there, but now I have this thing in the brackets here is sum range d plus 1, and so that should be HD. I can now rewrite HD, hopefully. Rewrite HD. And I can. And now fib d plus 1 is fib d plus 2. And so now the simplifier will do this, right? And it does. Because I taught the simplifier that fib of n plus 2 was fib n plus 1. And so in fact, I wonder when the simplifier started to be able to do it. So maybe here. Yeah, the simplifier does that. So maybe even here. Can I do that? Yeah, the simplifier likes that. And sum range suck. I wonder, let's go to the definition of sum range suck. There it is. Oh, it's not a simp lemma, which is quite surprising. Because I was going to say we might even be able to comment this out, because it looks like the kind of thing that should be a simp lemma. And now you see it fails. So let's do this there. So that works, right? So I don't really know, what's the best proof? Is this a good proof? It's harder to understand than the original one we had, but anyway. So what do I want to do? Let's prove Binet's formula. That's the thing I thought we could do. So Binet's formula. And how's that going to be? Well, I guess let's define alpha. Oh, we need to import the reals. Import data real basic. There. So let's define alpha to be a real, to be 1 plus square root of 5 over 2. And Lee's having a good think about this. Why don't I put a full stop there? Why is Lean having a good think about this? Let's try restarting it. Are we good? We're compiling. We're having a think. Oh, here we go. It's worked fine. So we don't have a square root, so I guess we should open the reals. Open real there. And now what are the complaints? And now it's complaining that definition of alpha is non-computable because the definition of square root is non-computable or something. Oh no, the definition, the issue is division, isn't it? Lean doesn't know how to divide by 2 because it's a bit worried that 2 might be 0, and it doesn't have an algorithm to check if 2 is 0 or not. So let's make this non-computable there, which means we can't eval it, right? Code generation failed. VM does not have code for alpha. So we've lost our ability to do evals. You see, we were evaluating up here, but you see, who cares about evaluation? So let's, there's my definition of alpha, and let's define beta to be its friend, 1 minus square root over 2. There's square root 5 over 2. And so now what? What's Binet's formula then? So here's theorem Binet. So this is probably going to be a challenge. Binet's formula says what? So let's have a think about what we're going to do. I guess we could state it. It says for all natural numbers n, alpha to the n plus beta to the n divided by square root of 5 the claim is that that equals fib n. There. Sorry. Because that's a nice easy thing to do, isn't it? It's probably worth mentioning that if I put this on this side, it doesn't work. There. If I put this on this side, then this doesn't work because this side is a natural number, so Lean expects this to be a natural number, and it finds a real number, and it's not at all clear. I remember when I was a kid being quite surprised that this crazy thing involving all these square roots of 5s was going to turn out to be a natural number. And so Lean doesn't have a clue why that's true, so we're full of errors, like we're just complaining that we're seeing reals and we were expecting naturals. But if we put this on the other side, equals fib n, then it works fine, because here it goes the other way. This is definitely a real number because it involves alphas and betas, and I'm claiming that it equals fib n, but fib n is a natural number. However, there's a very natural map from the natural numbers to the real numbers, and Lean is implicitly, you see, I could have done it. I could have put the little up arrow there. There you go, up arrow fib n. That would work. Now we can see the map explicitly. Even if I don't put this up arrow, then when we look at the goal, you can see the goal is there, right? You see, there it is. So how are we going to do this? I guess we're going to do it by induction again, right? Intro n. So do you know what? We need to do it by, we're missing a principle of induction, aren't we? So let's define induction 2. And what's that going to say? That is going to say we've got some family of propositions, so an infinite family of propositions, and then H0 is that P of 0 is true, and then H1 is that P of 1 is true, and then H suck is that for all n, if P of n is true, and P of n plus 1 is true, then P of n plus 2 is true. There. And the conclusion of our induction hypothesis is that for all n, P of n, I didn't get it for all n, P of n So before we can, because this is how we want to prove Binet. Yeah, this is how we want to prove Binet. We want to use this specific kind of induction. So let's prove that this induction works. So intro A, so intro N. So how are we going to prove this? Okay, I know how to do this. It suffices to prove P of n, P of n and P of n plus 1. Right? Because why does it suffice to prove P of n and P of n plus 1? The reason that's true is because if we know P of n and P of n plus 1, then we can certainly deduce P of n, right? So, I don't know, CC tactic will figure that out for us. So now we've got to prove P of n and P of n plus 1. And this one here, we can do this by normal induction, right? For all n, P of n and P of n plus 1 is true. So let's do induction n with DHD. And now the base case, it goes here. And the inductive step goes here. And the base case, let's have a look. We're supposed to be proving P of 0 and P of 1. And we have those, right? H0 is a proof of P of 0 and H1 is a proof of P of 1. So we can do exact H0, H1. There's the base case. And now the inductive step, let's see what we got here. We've got 4 spaces. Let's go back to 2 spaces. So how are we going to prove this? I guess, so we know that P of D and P of D plus 1 is true, so we could do cases on HD, right? Cases HD with HD, HDS. H suck of D. And now we can, this is a goal, we can split this goal. And now the top goal, we've got to prove P of suck D, and that's P of D plus 1. So this is exact HDS. And this goal, we've got to prove P of D plus 2. So here we can apply HS, right? Apply HSS. And now what have we got? We've got nothing. If I fail to delete, bingo. We've got, great. We've got 2 goals now, and they're both easy because one of them is HD. So maybe I should apply HSS D HD. Oh, now I've only got 1 goal, P of D plus 1, and that's HDS. So if I put HDS here, then this works. So in fact, this is exact, right? There we go. So now we have an induction hypothesis. So let's apply induction 2. Apply induction 2. There. Now, so this is where the work starts. This doesn't even look true. Let's try minus. I think that's got more chance of being true. The good old base case. Yeah, I think this is much more likely to be true because alpha to the 0 is 1, beta to the 0 is 1. Great, so we've got to do something here, right? Do you know what? We're going to need some lemmas about. We need a little API for alpha, don't we? So lemma alpha 0 says that alpha to the power 0 is 1, and I think that might be true by definition. It is. And alpha 1, alpha to the power 1 is alpha. That's useful, and that's not true by definition, which is kind of funny, but that's going to be called something, right? That's going to be called power 1 or something. Power 1 alpha. You see, the error says, no, it's not called power 1, because power 1 says for all a to the 1 is a. So this is going to be power 1 alpha. Great. And lemma, we need alpha suck. Alpha to the power of n plus 2 equals alpha to the power of n plus 1. Well, should we do it this way? Alpha to the power of n plus 1. There. Because we're going to need this, right? And it doesn't understand it because I didn't say what n was. Let's let n be a natural. And here we're going to have to do some work. So why is alpha to the n plus 2 equal to alpha to the n plus 1? Do you know what? Maybe the first thing we can do is lemma alpha 2. Alpha pow 2. Maybe we should call these pows. Alpha pow 0. And this could be called alpha pow 1. And alpha pow 2, this could say alpha squared equals alpha plus 1, right? We're good, right. Alpha squared is alpha plus 1. That looks like an important lemma. And we've got to prove this. And it might be tricky. Who knows? So I guess we could start by substituting in the definition of alpha. Where does that get us? Okay, I'll take that. What did I actually do? You shouldn't really do simps. Let's try this. Simp only alpha div power. So now I've got to prove that something. Oh, do you know what? We could have Lean must know a formula for a plus b squared. Is that called pow 2? That would be called pow 2 if I was writing this library, and I am writing this library to a certain extent. Pow 2, great. Oh no, not great. What about add pow? I want to do a plus b. Have we got an add pow? Oh, come on. Oh, add squared. Add pow 2. Is it called add pow 2? How about that? That's not a thing? No? What's example? A and b reals. I want to know why a plus b squared is a squared times 2 times a times b plus b squared. So we need to find this in the library. It's a squared plus 2 times a times b plus b squared. There. And it's having a good think. And this is surely in the library. I mean, I can live with it if it's not, but I'm pretty sure I've seen this in the library. Maybe I've made it too difficult making them rings. Let's try integers. Is that easier? Really? Oh, do you know what? What about a times a plus 2 times a times b plus b times b? All I'm hearing is fan. Okay, it might be not imported then. So let's go then. Rewrite pow 2. Actually, I want to clear denominators. Isn't there some field simps or something? Is that a thing? Field. How do I clear denominators? There's a ring. I thought it was field simps. Field simp. Let's try field simp. Will that clear denominators for me? Great. Denominators are cleared. And so now let's rewrite pow 2. And now let's simplify again and see what we've got here. And what's the problem? Oh, so we should expand out this. I really want this squaring. Rewrite add mul add. Is this a thing? Come on. Really? Very surprising. But what do I need now? I mean, I have to expand out the brackets, right? Rewrite mul add. So let's do some rewrites. If we're going to use pow2, mul add mul. How are we doing? We've still got another add mul. We could do a mul1, mul1, add mul, mul1. How about that? Oh, doesn't like the last mul1. Let's get rid of that. Oh, is it 1 mul? No, we're good. Oh, there is a 1 mul though. Wait, why am I doing this? I need to. The issue is square root of 5 squared, right? The issue is, so I need to do another. I need to do an add mul. I need to get to the square root of 5 squared. Bingo. Square root of 5 times square root of 5. Because that's the problem. That's the. I should say this. The ring won't do this, right? You might just think do ring. But you see that ring gets somewhere, but it refuses to simplify square root of 5 squared. So at this point here, we have a square root of 5 times square root of 5. And I guess rewrite, so what will this be called? Sqrt mul self or something. No suggestions. Sqrt mul? No. Sqrt mul primed? No. Sqrt mul? No. Oh, is this called sqrt or something? Sqrt. Do you know, I'd just be lazy. Example. X is a real number. And then hx, 0 is less than or equal to x. I want the fact that square root of x times square root of x equals x. Let's see if the library is any more forthcoming with this one. Bingo. Mul self sqrt. So I want mul self sqrt. Rewrite this. And now what? So I think now I'm in the situation where ring will work. Which it did. But now I have to prove that 0 is less than or equal to 5. A norm num will do this. Ah, I see. So maybe the thing to do here is, you see mul self sqrt takes an input, right? This is a function, but it takes an input. It takes an input x, which it says it will guess, and then another input, which it wants us to tell us. So show 0 is less than or equal to 5 by norm num. Or should I, do I need to put the reals? Yeah. Show that the real number 0 is less than or equal to 5 by norm num. And now I think, let's have a look at what we have. And so now there's no square roots of 5, there's no squaring anymore. And this should just be, this just says that like 8 plus 12 root 5 equals 8 plus 12 root 5 or something. So ring should be able to do this. Let's see if it does. It does. Wonderful. So there is the proof that alpha squared is alpha plus 1. And now the thing we need, the thing we're going to need is that alpha to the n plus 2 is alpha to the n. And so now this should be rewrite pow add. That will be a thing. Yep. Rewrite pow add. Very good. And now we've got an alpha squared. Rewrite alpha pow 2. there, and now are we there yet? Oh, let's try ring exp. There we go, that's done it. Great. Ring exp is a ring tactic that knows a little bit about powers. In fact, yeah, I see. The moment I rewrite alpha power 2, maybe I could even do that there. There you go, an even shorter proof. The moment I've rewritten alpha power 2, the ring exp tactic can do that. So there is a proof that alpha to the n plus 2 is alpha to the n plus alpha to the n plus 1. So now what are we doing here? Oh yes, our induction. So we've got 3 cases. So this one here, we should be showing that 1 minus, I mean, let's try simplifying it. It won't do it completely. There. What does the simplifier do? Oh, the simplifier does do it for us. That's handy. The simplifier did that one for us. Now the simplifier won't do this one. What does the simplifier think of this? Alpha minus beta over square root of 5 is 1. So if we tell it the definitions of alpha and beta, then how much further will it get? Right, hard luck. So now we know what to do here, right? I could squeeze this. There. I could squeeze this one as well, couldn't I? Just makes them run faster. If I squeeze simp this, I could do this. There you go, look at that amazing proof. There you go, runs much quicker now. So now what's my problem? My problem is this. So again, I want to clear denominators, field simp, and then hopefully ring will work, except ring won't work, will it? That's kind of interesting. We're close to getting ring working. I think ring will probably end up proving that something over itself is 1. Yeah, that's no good to us. Ring's taking us in the wrong direction. I think that we should perhaps apply a theorem that says a divided by a is 1. Div self. What's div self? Let's convert div. Can we do this? Self. Is there a div self? Div self, anyone? Div self ec1. Is that a thing? Div self, is that a thing? Ah, div self. Let's try convert div self something. What do we get now? Ah, this looks good. Because the first goal is some identity that doesn't need square root of 5 squared. So it's going to be a ring. And now the second goal is more interesting. Oh, it's especially interesting because it might not be true. Is it true? Let's try simplifying it. This is a bit annoying. Will ring do anything? No, hard luck. Let's try intro H, ring at H. How about this? Oh dear, dear, dear. This says 4 square root of 5 isn't 0. I think maybe we should have got rid of this at this point. Why don't we do that instead of this convert trick? I want to prove what I want to prove. I want A equals B implies a divided by b is 1. I think that would be nice. Let's apply div ec1. Is that a thing? Oh, bingo, div ec1 if ec. This looks good. Oh, let's rewrite this. This looks perfect. Let's rewrite div ec1 if ec. Ah, this looks great. And now, presumably ring will do this first one. It did. And so now all we've got to do is prove that 4 times the square root of 5 isn't 0, which is kind of obvious, but, you know, Lean is sort of funny like this. So I guess I could apply mul ne 0 of ne 0. This is called something like this, isn't it? What's it called? It's just called mul ne 0. Yeah, let's try applying mul ne 0. Great. And now the first goal says that 4 isn't 0, and norm num should be able to do that because it's about numbers that it understands. It did. So now this reduces to prove that the square root of 5 isn't 0. And hopefully this is a lemma, right? Because, you know, I don't want to start squaring both sides. I don't want to exact square root ne 0. Is that a thing? Oh, it might even be positive. Do we have square root pos? Pos. What about, let's try, is there a square root pos? Ah, square root pos. Bingo. So how about this? To prove that it's not 0, apply, let's first use symmetry. There, and now let's apply any of LT. There, and now let's apply square root pos. I can't do it. Oh, I have to rewrite it. Rewrite square root of pos because it's an if and only if. And now I've got to prove that 0 is less than 5. And so norm num will do that. And now what goes? That goes there, I think. Bingo. Everything compiling? No. Oh, that's because I've got too many. How about that then? Great. You like? You like. Wonderful. So, here's the hard part. How long have I got? I've got 15 minutes. I reckon I could be able to do it. Let's go. So intro n, intro hn, intro hn1. All these stupid square root of 5s. Do you know what? Do you know what? It would have been much easier. I'm going to refactor my proof. It would have been much easier we should have cleared these denominators right now. We should, how do I get this? Example, A, B, C. What do I want? Kind of A equals B times C implies A over C equals B. There. I want that. So I need C is not 0. Right, let's see if we can get this. Example, we haven't done very well with this sort of thing. Let's, example, K type, field K. Let's have A and B and C in K. We want, oh, and then H, and H is that C isn't 0. And I want A equals B times C, implies A divided by C equals B. What's that called? And if you can't find it, then I'm happy to use, you can find it. It's div if. I'm going to use div if before we even start. Let's rewrite div if. Oh, okay. Let's go intro n. Rewrite div if. Wonderful. Now I've got to prove that square root of 5 isn't 0, and I've just done that. And it went like this. It's this, right? It's that. So let's just do swap. How about this? It's just good to get, let's get the stupid side condition out of the way. It hasn't worked. Why didn't it work? Apply any of LT. Oh, hard luck. I'm going to have to apply GT. LT. Symmetry. Stupid computers. Any of LT. Bingo. This has worked. So now I want to revert n. There. So now we've got to prove the, I think it's going to be an easier proof now because now we have no divising. There. So now let's apply induction 2. And the first proof doesn't work anymore. I think the proof is easier now. Simp. Let's try simp. Let's get rid of this. Well, it certainly worked. And what did it do? It did this instead. So there we go. And now this one, how are we doing here? Oh, we've still got 2's in the denominator. But field simp, you see, this is good because field simp knows that 2 isn't 0. It doesn't have a clue about square root of 5 not being 0. But it knows that 2 isn't 0. And so now we can get rid of all this. And now can we do this with ring? Bingo. Oh, this is much better. Great. So now we've only got 10 minutes left, but we've got a much easier goal. So here we go. Alpha to the n plus 2 minus beta to the n plus 2 is yada, yada, yada. So I guess we could rewrite we could get simp to do this, couldn't we? Look, if we tell the simplifier this, there, and if we tell the simplifier, there's a problem, right? Have you seen the problem? The problem is that we haven't got the problem is we need all the API for beta as well. We need all of that stuff for beta. And I don't know how to do search and replace for just partial things. I know how to do it in Emacs, but I don't know how to do it in let's make all of these simp lemmas. And let's make these simp lemmas. And this one here as well, but this one doesn't work. I haven't finished. I need to change this alpha to a beta. And now does it work? This is kind of cool. It's thinking. The proof doesn't work. Hard luck. Rewrite power 2, mulad. Yeah. Oh, mulad fails. Oh, I see. It's mul sub now. Mul sub, that worked. Add mul, that worked. Mul 1, that worked. And now this looks to me like another mul. Is this? What am I doing? I'm trying to get to the I need to, it's submul again. I've got to get to square root of 5 times square root of 5. And I'm still not there, submul. So now I have, do I? I don't. 1 minus square root of 5, I'm still not there, submul again. And now do I have it? There it is, square root of 5 times square root of 5. And lo and behold, that proof now compiles. So finally, beta, yada, 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 says that beta to the n plus 2 is beta to the n, add beta to the n plus 1. And that proof compiles. And so now we might be in a good position to see, let's see what the simplifier does. Yeah, I mean, it's just done, I know exactly what it's done. It's just done rewrite alpha SS, beta SS, right? That's what it's done. And if we take a look at how are we going to do this? You know what, we've got this last fib n plus 2. Why don't we, what was it called? Fib SS or something? Yeah, fib suck. Let's call it fib SS. Have I used it yet? How many occurrences of fib SS are there? 1. Let's call it fib SS. There. And let's rewrite fib SS as well. Let's see how things go. Great. And now we want to rewrite add mul. Oh, and it's failed. Oh, it's failed. Curses, because the joys of real numbers. Huh. Let's try normcast then. Well, that's sort out. The problem is that the arrows, these secret arrows are in the wrong place. Oh, no, do I need to push them in? Let's try pushcast. Does that do something? Bingo, pushcast has pushed them in. So now rewrite. You see, let me just show you what happened here. We're dealing, fib n is a natural, right? And this is a real. And this little up arrow says, apply the function that takes naturals to reals. And so what's happening here is first we've got 2 naturals and we add up the naturals and then we apply the function that takes it to reals and then we multiply by square root of 5. So you see, so we can't use distributivity on the reals yet because we don't have the sum of 2 real numbers. We've got the sum of 2 natural numbers, then regarded as a real number. But if I push the arrows in, then this says, regard this natural as a real, regard this natural as a real, and now add them up as real numbers. So now this is the sum of 2 real numbers, so we'll be able to go back to our rewrite, add mul. There. And now we have fib, and now you see we can rewrite these. We can now finally use hn there and hns. And that will give us, no, somebody doesn't know, hn1. I should be consistent. And now I'm hoping, you see this doesn't look too tricky, does it? So I think that ring will do this. And it did. Great. So there's how to do Bino. That shows you how to do lots of things. It shows you how to work with reals. It shows you how to, I don't know. I think this is somehow illustrative because this is kind of harder than you might want it to be. But that's because there's no general tactic that deals with square roots. So we had to kind of constantly play with the square roots. And also, I also learned a lesson here is that one should get rid of divisions as soon as possible. Like, how many times have we divided by square root of 5 by the time we were down to here? And every time we divided by square root of 5, we were going to have to prove the square root of 5 isn't 0. So let's just do it at the very beginning. Right, my cat is meowing. So I'm going to have to go. Thanks for watching.